we start with the first day. So since 4 years, I think we have 1 day on quantum computing, and typically the sound is a little bit strange, right?
Yeah.
It's boring. Huh? Clemens is trying to find somebody. So the first talk, the first series of talks will be on quantum computing. Switch on. And my first talk will be on quantum applications are hybrid, right? In the meantime, so we run projects since 5 years, right? And the insight is at the very beginning you think a quantum algorithm is all you need, and I would like to explain to you that this is all bullshit, right? But quantum computing is an integration task that we in computer science do since many, many years, right? So, first of all, quantum algorithm, what is the paper version of a quantum algorithm? So what you see first is here's a very, very famous paper, the HHL algorithm. It's an algorithm that has an exponential speed up in solving linear equations. Very famous, very powerful, right? And at the heart of the paper, you have a lot of mathematics here. This is, so to speak, the heart of the algorithm. Right, and then the boring task starts that you need to transform the algorithm into a so-called circuit. Right, most of you know that quantum computing today is at the assembler level. That basically means you code assembler, right? And this is, so to speak, the quantum assembler. By the way, there is a language, IBM invented it, and some other companies blessed it. It's called QASM, quantum assembler. So welcome, computer scientists, to assembler again, right? So, and then the algorithm is also unitary transformation, because quantum computing is all about linear transformation in complex vector spaces. That's basically it. And then in the paper, in each paper, the physicists say something. We need an efficient procedure to prepare the input vector, right? The target vector A times X equals B. So we need a fantastic, efficient procedure to prepare B, right? And if you find something, nobody knows whether we got something, right, then I got an exponential speed up. So it's a little bit tricky and a little bit unfair. So that means you need to prepare the data. It's all about data. And pump the data into a quantum computer, right? We call it prepare the quantum state. And there are many different means to do that. You can pump vectors into it, set of vectors, matrices, categorical text data, blah, 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 QBOS, and some special representation of binary optimization routines, right? And that basically means, okay. It was too nice. So that basically means that you need to come up with an algorithm, so to speak, to prepare the state. So this is here now, the HHL algorithm looks quite simple, and then you need some classical pre-processing in order to generate a circuit that pumps the data into the quantum computer. That's called classical pre-processing. And that basically means one of the mechanisms how you pump data into it is this kind of circuit. You need to generate it based on the vector. Then you get the vector into this kind of a circuit. The circuit is then prepended to the proper algorithm, and then the algorithm can basically run, right? But you need this classical pre-processing step. And then the next thing is, at the end, if the algorithm finishes, yeah, you have a quantum state in your quantum computer. But the real world, that means the classical world, needs data out of it. So you need to measure the quantum state. And if you measure the quantum state, you get data that you can use in a classical manner, in a classical means. So you need to measure it. But measurement is also error prone. That means because measurement typically lasts longer than the computation, it is error prone, and then you get the distribution. Quantum computing most often spits out the probability distribution, right? And you need to interpret this probability distribution. What is the result of your algorithm? So this is the disturbed distribution, and what you are interested in is the correct distribution that the algorithm should spit out. And then you need to correct it, and, some sort of error mitigation. So, and what you then need to do is you need to compare this, and then the wrong distribution goes away and the right distribution is left over. And this is called unfolding, a special kind of error mitigation. Right? To apply some statistics
to correct the distribution. And this again requires classical post-processing. So we have pre-processing, we have post-processing, and what that basically means is, this is your measurement result. You apply a very strange matrix here, I come to that in a second, and then you get out the very fine approximation of the result. So what is this matrix? The matrix must be determined again by means of quantum circuits. So what you basically do is you prepare ideal states and immediately measure the states, and then you get the columns of this matrix. Then you invert it, and then you can apply this technique to get the unfolded, the error-corrected distribution. Right, so the overall structure of a quantum algorithm is, here's the heart, this is the real algorithm. You need to do some pre-processing, you prepare your data, you measure it, you do some error mitigation, and then this is also some post-processing, then you have the result. So that basically means is, here is the heart of the algorithm. This is, so to speak, somebody has seen, this is a BPMN diagram, right? This means here I go to a quantum computer, the hammer means classical tool, right? The gear means it's a sub-processor. We need to prepare a circuit, to compute a circuit, so that the data can be pumped into the computer, quantum computer. You need to prepend it to the algorithm proper, then you execute that on the quantum computer. You get a measurement out, you unfold the measured distribution, then you deliver the results. It's a little tiny workflow only for the algorithm, right? And then, of course, here this is a sub-process, blah, 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 and so Benjamin will tell you a bit more. But an algorithm is not an application. Nobody will say that a bubble sort is an SAP application. This is bullshit. Right? But today in quantum computing, most people say, I have an algorithm, this is a fine application, I can solve the problem, but we know that an algorithm is not an application. So here's a real use, a sketch of a real use case. It's some machine learning thing here. Right? So you need to prepare some data, you do some feature engineering, then you want to do some clustering. So and this again is now a workflow, right? You need to retrieve the data out of a database, right? Then you compute some sort, we apply some special computation, we compute the distance matrix, because this is categorical data, so text-based data that we get out of the database, and we need to transform it into numerical data, because all the many machine learned algorithms work on data, on numeric data. Here we compute then the covariance matrix, we transform something, and then we compute the eigenvalues, because we want to do a principal component analysis. And here is now a step, it's a sub-process where we use a quantum computer, very famous algorithm, VQE. Then we have, so to speak, done the feature engineering, then we do some classical pre-processing again, and then we go again to a quantum computer by means of another very famous algorithm, Quara, then we compute the different clusters. So it's a real workflow that you need, right? And only in two steps here we use a quantum computer in order to build the overall application that we have. So this again is here the sub-process and so on. So and then, if you have an application, you don't want to run it once, because you want to make money out of your application. That means you need to package it. What we have here is a topology diagram. Here you have a Java application that retrieves the data. The Java application requires a JVM to run. The JVM runs on the server machine. You retrieve the data out of your database. The database has been materialized in DB2, for example, that runs on Linux, that runs in a virtual machine. There's only a very tiny subset of the overall topology that you need in order to build the application. And what you do then is, all the artifacts that you need to be packaged into an archive, right? We call it a quantum application archive. It's based on a standard that IBM released together with others, Tosca, right? And we extended this a little bit in order to also store quantum artifacts into this archive. Then you have this archive, and then you need two kinds of orchestrations. You need the workflow engine that interprets the workflow that I've shown a couple of slides before. The workflow engine navigates through the workflow, and whenever it finds a step to be executed, then another workflow, another orchestration engine may jump in that we call the provisioning engine. right? It provisions, according to this topology diagram, the artifacts in the cloud, for example, or on-premise, so that then the overall workflow can be run. So the workflow engine interprets the graph of the workflow, and then the workflow engine invokes the code that is provisioned, deployed based on the topology diagram. So you need two orchestrations in order to make the application run. So then if you have this workflow, the classical parts, for example, what you do in a modern world, you use microservices or APIs, right? And that basically means here I have to retrieve, the workflow engine detects that this piece of code needs to be invoked. It's an API, right? Many people like Gartner say API is the new open source, right? Open source is no longer interesting, API basically is it. Then the API is invoked and the API is implemented by some sort of a microflow in a classical environment. And this microservice may use another microservice. For this purpose, you need something else, a data plane. You also need a control plane to find out where the microservices are. You might recall this is the old service bus, right? People complain, service bus is bullshit, I don't need it, much for heavyweight, but this problem doesn't go away, right? We have more modern technology to service bus, to smash it into different components. And then, how do you develop this overall stuff? You need to develop classical code. You need to implement quantum algorithms. You need to implement a workflow. You need to monitor your application that is run. We work with companies, right, where the workflows are running really for many hours up to several days. It must be bulletproof. How do you build this kind of an application? So we envision multiple life cycles that we basically have, and this will be the subject of Benjamin's talk. Will give you a first insight how to develop quantum-based applications. And then the big question is, when to use quantum, when to use classical? When does quantum already provide a little bit of benefit, right? And what are best practices to build quantum applications? So and this will be, we have a tool called QANA. It's called Quantum Humanities, right? But it can be used, of course, outside of the humanities. And we have some sort of pattern languages. And this will be brought to you by Johanna, Johanna. She will explain how these tools basically fit together, right? And then, on which available QPUs may my quantum program read, right? So if you have a quantum algorithm implemented in the circuit, you need to find out on which QPU, on which quantum computer can this algorithm already run. Because you need the number of qubits, you need certain coherence time and so on. And this is another tool that we are going to present, and this is what Mani will show you, right? What could be built here. And next, there is a project going on that turns this into an infrastructure that can be run in the cloud, and you already see some of the pieces that we present. There are patterns here, right? There is what Marie will present. This is the life cycle, how you use it, what Benjamin will do. And this overall platform will be presented to you by Michael Falkenthal, who is with the company Store One here. And then he will also talk about how to make money out of it. Right? Because if you implement a quantum algorithm, right, this is cumbersome, you put a lot of brain power into it and you want to sell it. For this purpose, first of all, you need some sort of a marketplace for this quantum application archives. It's like an app store where you can download the quantum application, provision it, then start it. Right? This will be, then of course you may pay for it. Some of the applications may be for free. And because the workflows use APIs, right, you need an API management piece of code so that the workflows that are buried into the quantum archives can go to the application, to the API manager in order to make money out of the implementations of your algorithms. So what you need at least is you need an API manager for the individual steps that are performed. You need a tool that allows you to model your artifacts, a topology modeler. You need to model your workflows. And then, of course, we have the underlying middleware. We have a workflow engineer, provisioning engineer, and we use some service mesh technology. This is a nice vision. Can it be done? So, and what we envisioned is that you put a request to run an application into a queue. The queue is basically backed by a queue controller, and the queue controller then detects that, well, I need to kick off a workflow, and the workflow will be fetched, the workflow entry will execute it. Some steps will invoke implementation of quantum algorithm, quantum circuits that run in a QPU. Some invoke pieces of code that classically run in the cloud. And then we wanted to prototype it, and what we have done is we have built a prototype with IBM. So we put the Camunda IBM engine in the cloud, and OpenTosca, it's a provisioning software into the cloud. And then the workflow run, as I said before, and then we use the so-called Qiskit runtime, where the algorithms are basically run and the circuits are then executed on an IBM quantum computer. And because BPMN is sometimes seen as old-fashioned workflow, who is interested in workflow, we made also a very modern implementation together with the company WSO2. Right? And here they have a tool that's called a low-code tool. Low-code is some sort of programming for my dog. Very simple. Everybody can do it, as we will learn tomorrow, right? And then the low-code has been what we have done is selectively for a few algorithms have we then used the low-code environment in order to run an application in the environment before. And this low-code environment will be presented to you tomorrow by Srinath and Walid, right? This will be the focus of tomorrow. And then, of course, is that only a dream? Some research prototypes, and what I've brought here with you is the newest development roadmap of IBM. What you see here is the Qiskit runtime. It's a special kind of environment where you can run combined classical and quantum code for higher efficiency. You also see that they are speaking about quantum software applications, so not only the algorithms are important, but the overall applications, and they even speak about workflows. The former slide was in 23, now it's in 26, I don't know why, but out of this scope, we will get a presentation this afternoon by Stefan Brunner from IBM, he's from the research lab. So, conclusion is real-world quantum applications are hybrid, that's what I wanted to show to you. Some such hybrid quantum applications require orchestration. You need at least workflows and provisioning technology. As a result, you need to package your application into new artifacts so that they can become tradable. The applications can be, of course, deployed on-premise, because sometimes you want to manipulate data that you want to keep secret. So parts of the application may, of course, be deployed on-premise. Others may be provisioned or deployed in the cloud or maybe in a mixed environment. And this building applications, this is something that I wanted to hammer into you, is an integration problem. Right? It's an integration problem that we computer scientists solve since 30 years. Right? Integration, this is it. And then the next talk will now. First of all, do you have questions? So typically, it's a SummerSOC tradition that you can even ask questions in between. Typically, the first talk is you may be different. You are a little bit shy, right? Wolfgang is typically when he starts, then he will kill me. Stefan, you have the first question.
Yes.
Speak up.
How big is the effort to get data input for
That's when it is. It's not simple. Yeah? Good?
Does it make sense that what quantum computing goes a lot of research required in order to make this work?
Oh, there are well-known algorithms that you can use. There are efficiency problems, or there are blah, 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 but it can be done. And Johanna will show this real use case that we had before, that you can even get precision increases that we could not realize on classical machines. So it can already be done, but it requires these DFG projects, Schwerpunktprogramme, but we can invent everything here.
Thanks for the interesting talk. One question from sort of an amateur's perspective in this regard. How stable is the programming model? I mean, that's the question. One has the impression, right, that the hardware implementations are still underway. It may not be completely clear, you know, how is the error correction actually going to work in the next generation of quantum processing units and so on. So the question is, how stable is the programming model? I guess the linear transformations remain what they always were. I guess it's still the same as is in this book, that's 50 years old now with Nelson and the basic quantum information book. That's all there. But the rest of it, how stable is that? Vis-a-vis the development.
So stable in the sense of, well, the development model, we need definitely, okay. So as of today, although I work on quantum computing since 6 years, if I recall correctly, I'm absolutely unable to invent an algorithm. This is something that physicists must do, or that mathematicians must do, but I can't do it. And then today it's hard to build circuits, and we need to abstract it, right? Because this is assembler, right? The computer scientists don't want to do it. So there's some research going on proper languages. What are the proper abstractions? People are just playing around. From my perspective, it's a just starting research field. How to develop that? Yeah.
But your data preparation steps, for example, they would be expected to remain rather stable. I mean, independently of how.
No, people may invent much more convenient ways to pump data into a quantum computer. But maybe we can ask that also this afternoon to Stefan. Yeah.
What about the latencies in accessing the quantum services? Because now it's cloud-based and you wait quite a while until it's returned.
This is what we mentioned, mentioned by the Qiskit runtime. What IBM invented is a means to store the classical code immediately in front of the quantum computer, so to speak, in order to avoid the latency, the communication between the classical code and the quantum code. And others picked this idea up. So this is really a fine thing, because you know that most of the algorithms are iteratively, mixture between quantum and classic. In order to speed that up, you package this classical code very close to the quantum computer with very, very low latencies. Thank you very much. Our next speaker will be Benjamin. Benjamin is a research sub-member at the University of Stuttgart. He's working on many different things, on simulation technology, using quantum and simulation technology, and on engineering of quantum applications. And he will now present some of his work in the area of software engineering for